Hello everyone. So this is the final topic of our unit number 3. In this particular topic, we are going to focus about the propagation of electric wave. Obviously, we could talk about the electromagnetic wave propagation inside a plasma or Earth's ionosphere as an application to it. However, to make our life easier, we will just think about the propagation of electric wave only through any of these things. So basically these things are related and therefore we will just study these things together. Now, let's recall. So this actually the model for these things would also be somewhat similar to as we discussed actually in the previous case, that is the model of an electron gas, which is sort of present into so this is sort of an electron gas which is being studied in presence of an electric field. And what is the nature of thermal nature of this electron gas is essentially it's a cold electron gas. Okay, so because it's cold, that means T is basically quite insignificant. Obviously, so that means actually their collisions are also sort of restricted. So with these sorts of things, we still know because we have more than one particles, they will keep colliding because their velocities are oriented along all sorts of directions randomly. So due to this collision could be modeled in terms of drag force for a given electron. So remember last time we had written the net force of an electron. So the net force experienced by an electron, so that was F drag. So this is basically the effect of medium, and according to us, this medium is going to be all other electrons other than the one on which we are considering the force. And then we have the electric force. Okay. So if we recall, that's all we had. So the drag force is going to be the mass of electron, the collision frequency, and then it will also depend upon how fast these electrons are moving. And then the charge on electron times the electric field will give you the electric force. Or that has given you R double dot plus 1 over tau R vector dot, that's minus E naught. We had considered the oscillatory electric field and that's it. Okay. So that was our differential equation. So the solution to this was, so remember what was the solution? So this is exactly what we had last time as well. So this will give us the drift velocity and that's going to be R dot, and the solution to this was basically minus E tau by m 1 minus I omega t and electric field. Okay, so that was my solution, and this was an approximate solution because we had ignored actually the very first term, that's a to the power, or let me just write it here. So that was a to the power minus t by tau. So that we had approximated to be equal to e to the power tau by, or rather I will just write in terms of frequencies. So that's going to be, in fact, let me just try to multiply it with this minus, or let me just write this as E by m, the electric field, upon multiplying by 1 over tau, so that's going to give you my omega c minus I omega. So that was the solution that we had, okay, for the velocity. So now R, what would be the R vector? Well, that's going to be the Vd dt. That means we need to integrate it again, and that will give us e to the power e by m omega c minus I omega, and E naught would survive. So basically we just need to integrate the oscillatory part of the electric field, and that means the position of an electron would turn out to be E by m, and then we will have omega, the mu c I omega. Let me use another pen. Looks like this is done. So that's going to be R is equal to minus E by m 1 over nu c minus I omega, and times, what is this? This will give you the integration as e to the power upon minus I omega, and then of course we had E naught as well. So that's going to giving you minus I omega is what we will multiply this whole thing by minus become plus, so multiply with I. So this will give us E by m. Then I will have a minus cancels, I square is basically minus 1, then we have another minus, so it's plus omega, and then we will have I nu c. Okay, so that's my expression for the R, the position vector. Now once you have the position vector, what we could calculate is the following. That's so with, of course, let me just write mu c was the 1 over tau, and therefore the polarization vector. So what would be the polarization vector would be? Now you remember polarization, that's from BSc first year, actually second semester itself. Polarization of the material will be minus Ne, which is the charge that's calculated through the dipoles. So, and then the distance. So minus Ne times R. So that's going to give you minus E by m omega plus I nu c times the electric field. And because we have Ne, so this is going to be Ne square. Now let's recall how this P appears for a material. So as you know that D is, you know that this relation D is basically, what is D? D, as you already know, is actually epsilon times E, which is epsilon naught E plus 4 pi P. Okay, 4 pi because of the Gaussian units. These may differ in different units. In SI units, it may be just epsilon naught E plus pi. Okay, now epsilon naught E is actually 1. So this is going to be 1, that's E plus 4 pi. Okay, so now let me just put the value. Okay, so epsilon E is going to be a common. I will just multiply by 4 pi and take the E common. So I will get 4 pi Ne square by m upon omega plus I nu c. That's it. So that's my expression for this. Once again, the electric field cancels, and therefore we get the value of the dielectric constant, the epsilon, the permittivity of the medium. So that gives us epsilon, which is minus, I'll just see here we have omega square sort of thing in the denominator. So the numerator should also bear a unit of omega square, and I brutally define this as omega b square, and therefore the omega, the denominator will be just as it is. So with what we'll have, what is the definition for omega p? Well, omega p is defined as square root of 4 pi n e square by m. That's my relation number 4. This is 5, and therefore n, the refractive index of the medium or material, okay, that's going to be square root of epsilon, and that's 1 minus omega p square upon omega plus I into c. Okay, so this is the expression for number 6. Omega p is, by the way, known as the plasma frequency. And as you could see, that if the number of particles or number of electrons into the medium, or essentially the plasma, the electron gas, or the ionosphere, if that's constant, then rest are anyway constant, so the plasma frequency is going to be the constant number. So what are the different things? We have omega c. Omega is what? Omega is actually the frequency of the electric wave. Nu c is the frequency of the medium, essentially the collision frequency. So now, depending upon these 3 frequencies, we may have 3 different cases. So now I will discuss those cases one by one. Okay, and let me in fact remind you that what was the definition for omega c? Omega c was 1 over tau, which was basically V thermal upon L, where L was the length of, or the dimension size of this actually conductor, or the gas, or of the vessel where actually this lies. So L, that's going to be L kT by m, where m was the mass of an electron. Okay, so now I will discuss the cases. So let me just take the very simplest case where omega is basically much larger than the omega p, okay, and also say nu c, okay. So this means the frequency of the wave is much more compared to the frequency of the plasma or the collision frequency. So in that case, let's check what would be the value of epsilon. So 4 would imply, 4 and 5, 4 would imply that, well, so omega p is smaller. So this is smaller than omega. Nu c is smaller than omega, so it's going to be roughly omega square. And then you will have omega p square by omega square. So that's the approximate relation. Or that would also, as omega p is smaller than omega, so this is going to be greater than 0, and therefore n, which is root epsilon, that's also going to be 0, greater than 0, that's positive, nothing special. So therefore this is called the dielectric domain. And what happens to it? So this is sort of as if the wave is propagating through the non-conducting media. So what happens over there? Some part is reflected, some part is refracted. Okay? Wave is partially transmitted and partially reflected. Okay? Now let's check. Nothing special. Okay? Let's now check the other case where these 3 things are get flipped. The first two things are flipped. That is omega p is greater than now omega. Collision frequency still stays smaller. So that could be ignored. So in that case, epsilon is going to be 1 minus omega p square upon omega square again. But however, this time omega p is greater than omega. So therefore, we should rather write we will essentially have this thing as negative. Okay, so this is going to be minus of, basically that's how I should write, so that everything over here is positive. Okay, so now this is actually positive minus 1, positive than greater than 1 minus 1, so this is a negative thing. Okay, so this is less than 0, and therefore n is going to be, n is root epsilon, so that's negative of this whole thing, and that's going to be I times root omega p square by omega minus 1, so that is imaginary. Okay, so due to this imaginary nature of the refractive index, we will see the electric field. So therefore the electric field, let me see what happens to the electric field. So this is e to the power, remember that's how you write, so this is just e naught, e to the power I k dot r minus omega t, and if we imagine the propagation is happening along the z direction. Okay, so that would mean, or let's write this as E is equal to E naught. So imagining that the propagation is along, so that will have E to the power. So let's say we will have the transverse component, okay, K perpendicular dot R perpendicular. Okay, I will tell what they are. So R perpendicular is basically x hat, y hat. K perpendicular is kx hat, ky y hat. Plus, so obviously we will have the third component, so that's going to be z hat. So this is going to be kz, and then we have the z. Okay, so that's it. And minus, obviously we will have the omega t, the auxiliary part. Or E is going to be E naught. Well, so let me just write the parts that are not affected. Okay, minus omega t. And now what is my kz? So kz is basically going to be, as you know, k is omega by c and n. Okay, in our case this is going to be the Plasma frequency. So that means omega c by n. So that is going, so I will just put the value of this kz. So that's going to be e to the power I, and then I root omega p square by omega square minus 1. Then we had upon c, omega p upon c. Okay, so that means in the next, and of course we will have z. So that's going to be E naught, and then we have this attenuation factor. So e to the power minus I square minus 1. So that's going to be omega p square upon omega square minus 1, omega p by c. So this whole lot of factor times z, e to the power k perpendicular r perpendicular minus omega t. So the wave will get attenuated along the direction of propagation. Okay, and this is the attenuation factor. Okay, so this clears that ultimate, so that because of this attenuation factor, the wave will basically sort of lost. Okay, so because of this attenuation, so this is over time, and that is the electric wave. Okay, so wave is kind of, so that therefore this is also known as the Evanescent domain of the medium. Okay. Now, let me just take the final case, which is basically, so now we had omega greater than omega p is greater than omega c. In this case, what I'm going to do, I'm just going to flip the omega nu c as well. So this is still going to be the second case. However, what I will have, I'll just flip. So what I assume is that omega p is still large. However, this is something like this. Okay. So basically what I mean is this mu c is larger. Okay. So in that case, so therefore the omega, so E epsilon is going to be, what was epsilon? That was minus omega p square upon, well, it is just like this. Okay. The collision frequency is greater than omega. Okay. So omega p square upon omega plus I mu c. So that could be approximated as, so now omega is small. Okay. So therefore this is going to be omega p square omega I mu c, or in other words, this could be actually of something like 1. This could be replaced with I square, so I cancel, so this is 1 plus I omega p square by omega nu c. Now, because omega c is quite small, okay, so this would be approximated as I omega p square omega nu c, as nu c tends to 0 actually. We had already seen, because it is a cold electron gas. Okay, so because of these things, we could have the refractive index. So now the refractive index would be square root of I, and then the square root of this whole thing, which in turn would be, so you know this is e to the power I pi by 2, square root of this is going to be e to the power I pi by 4, and therefore we will have this. Okay, and then we will have omega p square root omega nu c, or in other words, this is going to be omega p root 2 omega and nu c. So that's my refractive index, okay, in this case. So what does it mean? It means that beta is going to be alpha, okay. Skin depth, you will have delta, which is essentially 1 over beta, that's root 2 omega nu c upon omega p. So what happens into these cases when the both components, that is the real and imaginary part of the refractive index, becomes the same? If that is so, in that case the wave is fully reflected. Okay, wave is fully reflected. And what does it mean? It means essentially it has, so let me just write actually, if you wish to write, omega p is lighter. This means basically it is kind of allowing, it is kind of killing the waves, which, so that means it acts like actually a high pass filter, that is the waves with only omega larger than the pass. So this means it's, the medium acts like a high pass filter, okay, with, of course, with critical density. What would be the critical density? That is calculated using 4 pi n E square by m is equal to given by omega p square. Okay, so NC is m omega p square by 4 pi E square. So that's called the critical density. So if n is smaller than NC, wave passes. If n is greater than nc, wave is fully reflected. That's what we get actually through these things. Okay. Now let us now try to apply actually what we have learned so far onto our Earth's atmosphere, and that would actually close this topic. Okay, so let's just think about what is happening to the Earth's atmosphere. So the upper layer of Earth's atmosphere, okay, so this obviously has nu c tends to 0. Okay, number one. So initially so medium is sort of transparent. So that means dielectric domain, like dielectric domain, wave is transmitted to another layer. Now the wave is transmitting to another layer, and that means what is happening into another layer? In another layer, because of, so the layer is denser. As the layer is denser, as the other layer has n above nc. So that means what would happen? So the wave, okay, so the wave has, as the layer has density larger, as larger density. Okay, so that means the wave will start. So that means that is n is greater than nc. So it means it will act like a high pass filter. That means cut the ionosphere, will cut waves with omega n of omega p. Now the third thing, now because you are cutting the waves, the reflected waves will turn back and of course heat the medium, right? Because they will have some energy, will turn back, and due to their energy, these will heat the medium. Okay, and what happens when you heat the medium? That means nu c would rise. Okay, so this means nu c, which was basically m by, V thermal by L, so that means root kBT by M1 over L, so that will rise, so that means we will move to the third range, so the third regime, okay, that is nu c becomes greater than omega. So once again you have a high pass filter like we have here. So this whole, to summarize, so initially although we could see the passage of electric waves because initially the medium is quite transparent, but as the waves moves on, it reaches into medium where the critical density, the number of particles are much more than the what we should have, which is known as the critical number of particles, or essentially the critical density, because these are the particles in certain area, unit area. Okay, so due to that, essentially we pass through a situation which doesn't actually allow the waves to pass, and therefore we have sort of the waves will get reflected back. Okay, and those reflected waves will heat up the medium, and therefore the mu c will rise, and therefore ultimately you will have the high pass filter like behavior. Okay, so this completely clears why we only receive the cold electric waves, which are sorts of quite useful in many ways to our lives. Okay, so I believe this completes the whole unit 3. By now, from the next time onwards, we will apply some of the interesting features of the reflection and the transmission that we had studied for the electromagnetic waves, and will try to think about actually devices where we could transmit these electric and magnetic waves, or essentially the electricity and magnetism, without losing too much on either of these components. And those things are essentially known as the waveguides and optical fibers. So that is all about the next unit. We will be talking more on those things starting the next week onwards. Thanks a lot. Stay safe and keep learning as much as possible. Thanks.